I think I will start. Okay. So last time what I argued was, okay, the classical configuration space suppose it is Q, and let us denote these points by Q. Then let us say wave functions, okay, psi can be thought of as functions on, let us say, Q cross a circle, okay, even in elementary quantum physics. Okay. So my wave function will be a function of a pair of points Q, let us say some point in this circle, let me call it omega and S1. Okay. So this gives you a complex number. In ordinary quantum mechanics, but I should insist that such that all wave functions obey, okay, psi Q. So multiply this omega by a phase. So this omega is of modulus 1. So it is a complex number with modulus 1. So if I multiply this by a phase, I pull out that phase with some, say, n theta, n fixed, n is z fixed. Okay. Suppose this is the case. This in ordinary, even in ordinary quantum mechanics, if I do this, I take into account the phase dependence of the wave functions. But if I do this, then it is clear that psi star chi, okay, is a function, is a probability density on Q. Okay. So it makes sense because it has no dependence on this phase. Okay. But at this point it is looks like a useless activity. But then we found that we can do more generally. Okay. Psi, okay, may be a function on Q bar. I gave you an example which only locally is Q cross S1. Okay. It may not be Q cross S1 globally. I gave you an example, I will remind you again, such that, okay, but okay, it has, okay, a phase U1 action psi. I can multiply this by this point of Q bar, so that there is some way of multiplying this Q bar by a phase, okay, so that psi star psi or psi star chi a function on Q. This is what I said yesterday last time, and I give you an example, and I am going to go back to that example. We saw the example, okay, is Q bar, and this is a very good important example. It's a pair of points, complex variables, such that normalization is true. Okay. And the phase, okay, so this is a three-dimensional sphere, so this is a three-dimensional sphere. By taking the real and imaginary parts, you see that it is a three-dimensional sphere, and on this clearly, okay, there is a phase action, okay, defined. I just multiply each of them by a phase. This does not change anything here. And Q in this case, I told you Q, okay, parameter is given by Q must be invariant by this phase action, okay. So it will be given by simply Z, the points in Q are simply Z dagger tau I Z, tau Z, call it N, because the phase cancels out. And we saw also, I said at least that N dot N is 1, you can calculate it. So this is a 2 sphere, so Q is a 2-dimensional sphere, okay. So when I look at wave functions on this space, which have the property indicated here, but the same N for all wave functions, then when I compute the probability densities, this phase disappears, okay, and I get ordinary classical standard interpretation of probabilities. But however, I cannot get into the phase in the wave functions without introducing complications, because it is not true that this Q bar is this space here is Q cross a circle. It is not true, okay. And I also showed you, okay, and now I will go to note, okay, that I can represent this Q bar, I can is isomorphic to, okay, this set Z1 Z2 minus Z2 bar Z1 bar, okay, which is an element of SU2. That is, these 2 by 2 matrices, this is a 1-to-1 mapping. Give me an SU2 matrix, take the first column, call it Z1 and Z2, or conversely give me a pair of complex variables, I can get an element of SU2, okay. So SU2 as a manifold is a 3-dimensional sphere, and this mapping Z going to Z exponential I theta is the same as an element here, they call it G going to G exponential I sigma 3 theta. I showed you also this, okay. This is what I had done last time.
G is an SU2.
Huh?
G is an element of SU2.
This is an element of SU2, okay. So what I had done. Now I want to look of in a concrete physical situation where this occurs, okay. So I will go through that exercise, and then we will see that if I want to quantize that system, I have to know something about Dirac's theory of constraints. So I will review it and apply it, and then we will consider magnetic monopoles, then consider multiply connected spaces where all these things happen, and that will lead us to QCD. So I want to look at a very simple system. of a non-relativistic particle with fixed spin.
What do you mean by fixed spin?
It has only one, the square of the spin vector is fixed. So let me show you. Okay.
But that is true for everything, every part.
No. Yes. But normally what people say is that such systems cannot be represented classically, because to get a classical limit you need very large spin. This statement you find in the literature. Okay.
Now suppose I have an electron.
It is only fixed spin. I agree with you. I am not agree. So if you want to make a classical description of a particle of fixed spin like electron, and you try, then you will find that as a particle, not as a quantum field, you will find difficulties because of the reasons you will see now. Okay. So let me look at the Hamiltonian formulation. So this is, I am now looking at classical. We will do quantum theory later. So it is spin. So we start with, we consider three spin vectors.
So now are you thinking of spin as just angular momentum?
Yes, spin vectors, say SI, okay, with, okay, we need Poisson brackets, okay. So now normally I write SI SJ is epsilon I j k s k. Okay. It's classical, so there is no I. Then, and I will also set S dot S is lambda square, where lambda is a constant. Okay. So this
Angular momentum.
angular momentum with fixed length. Okay. It's not orbital, because there you don't, so 2, okay with 1, since the Poisson bracket SI with S squared is 0. So classically there is no problem as of now. This is the way I will represent this system classically in the Hamiltonian formulation, and the equation, depending on the equation of motion, okay, if equation of motion is dSi dt is 0, so I am not worrying about its translational degree of freedom, then H is 0, Hamiltonian is 0, right? Suppose I put it in a magnetic field, okay. So if there is a it could be a constant, okay, up to 0 or constant.
It's
Okay.
a constraint.
Hamilton 0, nothing happens, no? Because the Poisson bracket of SI with 0 is 0. But if I have if there is a magnetic field, B, okay, I choose my H to be say mu S dot B, right, and let us check it works. Si with H, so Si dot with is a Poisson bracket Si with H, it will be mu, right, Poisson bracket Si with Sj Bj. So you can see that this is okay. Is I epsilon I j k mu S I S j. What? I'm S I epsilon I j. I'm worrying what happens to the index k. What is this? This is SISJ. Oh yeah, SK, right, okay. BJ SK. SISJ is epsilon IJK SK B, right. So this is okay, right. This is mu is a magnetic moment. So this is simply saying this is B cross S. So S dot is B dot S, B cross S. So the spin rotates around a magnetic field with some Lambda frequency which is given by this mu. Everything is okay. Looks very trivial. So we assume that we have done the whole job and we can go home. Okay. Sorry?
If the equation of motion is ds dt is equal to 0, it follows that the Hamiltonian is 0.
Constant. Yeah, because there are only the full set of degrees of freedom is Si. There is nothing more in the system. Okay. So it can only be a constant, which constant we cannot fix anyway. Okay.
And I just record that it commutes with S. That's what.
Yeah,
So it has to be
constant. Yeah, but constant you can renormalize, subtract from the H.
provided you think of spin as the only degree of freedom.
This is the only thing here. That is all I want to consider. I want to consider extremely simple systems where complications start happening. So what is the complication here? The complication I ask is, I ask you, what is a Lagrangian for this system? This is a Hamiltonian formulation, but I suppose that I want also to find out the Lagrangian formulation. This idea that I am going to now develop actually plays a very important role by the time you come to quantum field theory. This you might have heard about this Weissenberg-Witten terms and so on. It's all this. Okay? It already is here, and I will show you how it happens.
But in this formulation we have not defined momentum. Canonical momentum has not been defined because of the trace.
All that you need for setting up a Hamiltonian formulation are not positions and momenta, but a Poisson bracket which is not degenerate.
Yes, but how do we convert that into a Lagrangian term?
That is what I am going to say. Okay? That is where the problem is going to arise. Okay? So, question is, if we can find a Q and a P, okay, with Q, so QP, okay, Q is a function of S, P is a function of S, okay, with standard Poisson brackets, so such that QS, PS is equal to 1, etc. If I can replace the S, there are 2 degrees of freedom in S. So if I can find 2 other degrees of freedom, then I can make a Legendre transform and get the answer. We can Legendre transform to find L, right. We will write L as P q dot minus H. Yes, where what is it, dH over dP, q dot will be defined by this inverse Legendre transform. So we will write dH over dP, I think will be q dot. I do not guarantee signs. From the one of the Hamiltonian equations is a definition of q dot. Okay, so you use that and go back and you are done. But the problem arises because S2, the 2 sphere does not admit global coordinates QP.
But you can use patches.
So yes, so I cannot at least unless I go into finding Lagranges in patches and all kinds of things, which will be a higher order activity, I cannot find a global Lagrangian. I can find a global Hamiltonian, there is no problem in writing the Hamiltonian, but I cannot find a global Lagrangian, okay, which is defined on a configuration space. So this method fails.
But then, if, for example, any system which has say SO3 symmetry, some spin system, some rotation, so the configuration space is S dot S to be constant.
Yeah, we will have the same problem. So this problem occurs not only here, but for example if you want to have a description of quarks with a definite SU3, okay, and goes on escalating, and we will see the same problem occurs for magnetic monopoles, and the same problem occurs in conformal field theories in 1 plus 1 and so on, and in script.
System like a rotation.
Yes.
So whenever there is a S dot H equal to constant, I mean some Sn is the configuration space. This problem will come.
Whenever you have a configuration space, okay, which is not moment you have a configuration space, whenever you have a phase space which is compact, you will have this problem, okay, because we come back to that. Suppose there were a configuration space Q, suppose there were a configuration space Q for the Lagrangian, then the Lagrangian is a function on positions and velocities here, right. So Lagrangian is a function on Q and Q dot, okay, and it goes into real numbers. So that L Q Q dot is a real number, okay, but the velocities are unrestricted, it is a tangent to a point there. So the velocity space, okay, is non-compact. So you see immediately that this topology of Q, the Lagrangian is defined on Q cross some non-compact space, okay, is actually what they call some, so TQ is non-compact. T means the tangents, Q and a space of all tangents, this is not compact, okay. It may not be of the form Q cross something, okay, it may not, but it is not compact for sure, because at each point the velocities can be arbitrarily large, even if Q is a sphere, okay. So the moment you find a compact phase space, you are done for, and you will not be able to find a Lagrangian, global Lagrangian, okay. That is not a sufficient condition, but the cases you mentioned, this is what happens. Okay. There are other cases where there are other obstructions which screws up the whole procedure. Okay. But there is a general way of overcoming this procedure, which brings us to gauge theories. Okay. So we could have told immediately that there is going to be a problem, because the phase space here is compact, that is a 2 sphere. Okay. There is some should split into 2 parts, okay. One part of which is not compact locally. Okay. Okay. So the statement is the following, okay. But still we can find a global Lagrangian okay, by enhancing degrees of freedom. I will show it to you. Okay.
So you can use some auxiliary field.
It won't be an auxiliary field.
That will also work.
No, it will not. I don't know whether it will work. I don't know of an example.
Add to a constant on that field.
I don't know of an.
I think, for example, if you use a Stuckelberg kind of grid here.
Oh, but this is a particle mechanics, so you can't do that. The particle mechanics. But I have seen some examples where people get around this problem by using anti-commuting variables and stuff like that. Okay. Clifford algebra. But
No, I don't know. I was thinking about field theory also. This kind of problem may arise. So there you can introduce auxiliary field. We'll write down
Yeah.
the Lagrangian and put a constant on that field.
yeah, but you cannot get this kind of thing by constraining in a trivial way. You will see why. Okay. You will eventually get this by constraining, but in a highly non-trivial way, and it will lead us to this entire issue of fiber bundles. Okay. So what do I do? Okay. So let me. Okay.
So, you said S2 does not admit global coordinates Q.
Global.
S2 does not admit global coordinates Q.
Yeah.
But is S2 the phase space or is S2
S2 is the phase space.
S2 is the phase space?
Ah.
So where is
S2 is the phase space because it is symplectic. I given you a Poisson bracket. It is non-degenerate. So it is a phase space. But it is not.
what is the configuration space?
That's what I tried to find out. It does not have the interpretation for a particular. You cannot split it into a configuration and momentum space. Impossible. There is no such description here.
So phase space cannot be
Split like that. So in that case, how do I find the Lagrangian? Okay. It cannot be done. Guaranteed, because if it can be done, you will get into contradiction of the kind I am telling you, that it will automatically have a some non-compact direction, okay? Some splitting, so that there is some non-compact flat direction, namely the velocities. So any phase space, okay, or any configurations, if you have a splitting of the configuration space into 2 parts, positions and velocities, that kind, then automatically the phase space. So you have. I will come to this. Q may be compact. For example, S2. Q is S2. Still, at each point of S2, what will happen is the velocities can be arbitrarily large. So there will be the possible velocities will be some 2-dimensional R2 at each S2. Likewise, here at each point of Q, you get momenta which form an R2, 2-dimensional real vector space. Okay. But if the manifold you are the phase space you are looking at does not have this structure, you cannot find these things.
So is it generally true that a compact manifold cannot be written as a Cartesian product of two non-compact?
No, of course not, because topology continuity will completely screw you.
But if I use relativity, then my velocity is not unconstant. There is a maximum velocity.
No, because there the problem will come. Somebody asked the same question in my group theory course. I think, I don't know. Because what is relevant is in the Lorentz group, what you are getting is things like V divided by, right? So velocity is V over C, 1 minus V, things will start blocking. So same problem, this is much more interesting is, suppose I take a particle of arbitrary spin, the relativistic particle. Can I write a Lagrangian and quantize it and get it? The answer is yes. For any spin, how will you do it? It's highly non-trivial. Okay.
Let's see the classic.
Okay.
So could you just explain how S square is the phase space here? As an idea?
Because S2, not S squared, S2. It's not a sphere, it's just a two-dimensional sphere. Okay. Surface of an orange. Okay. Because phase space means that between the functions on that space, I can give a Poisson bracket, okay, which is which fulfills Jacobi, is antisymmetric in Jacobi identity. Okay. So I have done that. Namely, the Poisson bracket will come by this equation, Si Sj, that equation. So you take any function of the Ss, and so if you give me some f1 of S, f2 of S, Poisson bracket will be the what does it go? The epsilon ijk, yeah, d. You can actually and you don't have to worry about the constraint, because the constraint will be automatically taken care of because of this epsilon. You put S squared here, you get 0 always. Okay. Okay. So this is a possible. I give you this bracket. You check Jacobi identity. You know Jacobi identity. 3 of them. This is antisymmetric in F1 and F2, and the plus B CA plus C AB must be 0. This is necessary, okay? But this will fulfill it because this is angular momentum algebra. Okay? So it automatically will fulfill it. Okay? So once I have given this between functions on my underlying space, that space is a Poisson manifold. I mean, you can write Poisson brackets here. You can call it a phase space. You can quantize, do everything. Okay? Okay. So the issue is, how do I find the Lagrangian? Okay. Huh?
How do I see that it's a Poisson manifold? How do I see that it is S2?
I put S squared equal to 1, lambda squared. 3 real variables, classical 3 real variables, and they fix their length. Yeah.
So here you have a problem with going to a global Lagrangian, right? Given a Hamiltonian. Is it ever a problem going to the Lagrangian to the Hamiltonian?
From the Lagrangian to Hamiltonian, a lot of problems because of constraints. Because when you go back this way, you will get extra degrees of freedom. You will see, okay? It becomes a gauge theory. But not a trivial gauge theory, but a highly non-trivial gauge theory. This is the simplest example of a whole class of things which go all the way to field theory, quantum field theory, gravity, everything. Okay? And when you go backwards, I will show it to you. as when once I have looked, it's very difficult because you get constraints, that is the so called Legendre map. You have extra degrees of freedom in the Lagrangian, you have to get rid of them. So the what they call Legendre map, the Legendre transformation is to a submanifold of the cotangent bundle, okay, and that creates a lot of problems. There is a schematic way of handling it due to Dirac, but it is really schematic, and later on when you apply it, start applying, I shall show you, as I will show you, it becomes an art rather than a set of rules, okay, on how to what to do. Huh? The relativistic free particle also has this problem. Okay. But that set of problems is a different, yeah, you had synced one way from Hamiltonian Lagrangian, it comes back and hits you in another way. Okay. It takes its revenge. So here, okay, what do I do? Let G be an element of SU2. Okay. So my Lagrangian L will be, okay, a function of G and G dot, the dg dt, that is what I will call as T of SU2. It will be positions of, but it will be on this larger space. So what is this Lagrangian? Okay. So what is, no, yes, okay. In Lagrangian framework, okay, is defined by say S is equal to lambda, so S is trace of sigma I, let me call it like this, sigma I G sigma 3 G dagger. This is a typical formula which comes all over the place. This is a definition of SI. The way, or if you like, or S dot sigma, sigma dot S is the same formula, is G, I should have lambda here, lambda G sigma 3 G dagger. This is my definition of S. S is not the basic variable of the Lagrangian. S is defined by this equation. Okay. Now from here you can see, okay, from here this implies, if I take the trace here, trace of sigma dot S squared, which is like twice sigma dot I think S squared. Sigma is sigma, j trace is delta I j times 2, okay. This is equal to lambda squared times trace of sigma 3 squared, okay, which is twice lambda squared. So the constraint is accounted for. Here, this one, twice S dot S. I just expanded it and I use the fact that trace of sigma j is twice delta ig. I got, so you see that I don't have to worry about the constraint. Now how do I find L? Set. Now I lambda, I give the formula G inverse G dot, okay, plus mu S dot B. So I have magnetic field. The first term, okay, so this has two terms. So let me call this L, let me call it West Zumino plus L0. The first L0 depends only on S. But the first term is a different thing altogether. Okay? This L West Zumino is West Zumino. Okay? This is stands for West Zumino for historical reasons. Rather, this term was discovered much before West Zumino by people doing geometry quantization. Okay? Kostan Suryo, actually Kirillov, all these people had it. Okay? But later it was rediscovered in quantum field theory by these two people. So people doing quantum field theory call it this term. Okay? But the history of this term is much more ancient. Okay? And it is a topological term. I will just tell you. I should say that we, our own group discovered this by messing around. I should say that's a correct word. Messing around, trying to find such a thing, independently of West and Zumino, by working with people from Italy and so on. And I should also confess that my promotions were based on this term. Okay. So by this I became a full professor. Not bad. Now, this is a very peculiar property, okay? And I will come back to that property as I keep going. Okay? Notice the following. Note.
So you just gave it as a prescription.
For some reason, I remember how I gave. At that time, this was, we are talking about early 70s. There was a flurry of activities for finding supersymmetric point particles and so on, and also how to describe point particles in the particle physics community. And there was a paper, even now it is by a student of Wong, somebody called Wong wrote Wong's equations for a point particle with color charge, internal degrees of freedom. He wrote the equations of motion, but he could not find the Lagrangian. So we got involved. We wanted to know what was happening. So we messed around, basically messed around, and eventually found this term. And once we found a lot of people, Mukunda was involved in this later to understand it. Okay? Because this is some very peculiar term. I can give you the geometrical interpretation, but now I am going to be for a while very opportunistic. That is, I want to give you the technology of these things. That's what you wanted. Okay? But if you want to become idealistic and really want to know the deep things, can be done. Can be done. So what is the peculiarity here? Okay. So I want to note something about this. Suppose I take g of t, the Lagrangian, and I make this transformation. I multiply it on the right. It's important to notice right and left. I multiply it on the right by this transformation. Now you see that S doesn't change. Why? Because the definition of S is such that this term cancels out in the middle. Okay? S is independent of this transformation. But what happens to L resume, goes into I lambda trace sigma 3 exponential minus I sigma 3 theta, right?
What? Did you guess that Lagrangian?
Sorry?
Did you guess that Lagrangian, or you have some way of tracking it up? That
How guess?
Yeah. Did you guess?
No, the best thing is to guess. That's clear. But there is something. He will object that I am being too idealistic. So there is something that if for example SU2, which is a Lie group, acts on the two-dimensional sphere. Okay, two-dimensional sphere is an orbit in the represented in the Lie algebra. You understand what I mean? Take sigma 3 and rotate. Then there is a theorem due to Kostad and Kirillov that these orbits are always phase spaces, okay, and allow what they call a symplectic form. There is a Poisson brackets, and there is a way of constructing this one form. This is like a PDQ of that symplectic form, and people know how to do it. There is a way of doing it. Okay? I can explain, but it will deviate me from where I am going. I will come back to it. So you don't have to, no longer do you have to guess it. Let me put it that way. One knows the technology behind it. But I want to know what happens here. Okay. So I have G inverse. There are two terms, right? G dot. Okay. Well, I can have G dot exponential I sigma 3 theta plus G times I differentiate this, okay, I sigma 3 theta dot, right, exponential I sigma 3 theta. Okay. But this term, first term, by the cyclicity of the trace, this cancel. So the first term is again L residue. Plus how about this term? Well, this again cancels with that, but now G and G inverse cancel. So I get plus I lambda, then I get I trace, okay, wait, sigma 3, wait, sigma 3 squared theta dot.
Oh no, two I's. That's right.
So this is L residue, minus 2 lambda theta dot. Okay. So the whole Lagrangian changes by a total derivative under this transformation. So L changes, yeah, by a total derivative. That's not only this, under G going to G exponential I sigma 3 theta. Okay. So at the level of equations of motion, this degree of freedom will go away. Okay. So in equations of motion, we expect only S and S dot, right? Because this is changing by total derivative. So let me check that out. But then I will show you that this is true, but suppose you try to eliminate this extra degree of freedom from the Lagrangian, you will get into a mess. Okay. So it is not true, I mean it is true that changing by total derivative, but if you try fixing the gauge, what they call fixing the gauge, you will get into a mess. Okay. You can, but then you will get introduced singularities or patches and all kinds of baroque things will come into the play. Okay. So better not do it. Okay. So this global Lagrangian is something which you will see later, does not allow you to fix a gauge, but still equations of motion are perfectly okay and you can quantize it. And when I do the canonical transformation and so on, you will find that I will get back the classical, the system I was talking about earlier, provided I apply the Dirac procedure in an appropriate way. Okay. So let me check the equations of motion. How will I do equations of motion? Well, you can introduce local coordinates, but I will not do that. We know that the most general variation of G of T, G is an element of the group, so the most general variation is by multiplying it, let us say on the right, okay, by element of the Lie algebra, right? Sorry? Small variation. The most general small variation I can do, for equations of motion I want small variations, and the most general one I can do is to multiply it by an element of the angular momentum, which is time dependent. That is all I can do. Okay. So let us see what will happen if I do this. Then the variation of the Vidya-mitra term, which is the first term there, we know that it is going to be I lambda trace sigma 3. Okay. You can see in the variation, if I do not differentiate epsilon, it will cancel out, because this is, they will come epsilon and minus epsilon, they will cancel out. So I need to bother only of the epsilon dot term G inverse, okay, I epsilon dot T, this is a vector, okay, let us write sigma I, right, I am doing the times G. Okay. This is a variation of the first term. So I do cyclicity of the trace, is I lambda, I put G sigma 3 G inverse, which is trace G sigma 3 G inverse. So okay, from here, okay, there is another I, so you get minus from here, then I get sigma I times epsilon I dot. But this is equal to lambda times this is what I call S, right? So it is minus trace S dot sigma I epsilon I dot. So this is up to lambda introduced, so it is minus, but this is going to be twice Si epsilon I dot. Now what about the other one? This is the first variation. So delta L0, which is delta of mu of S dot B. So S I have to vary. So I need to know what is. Remember that Si is I should get S right. S dot n, what is it? S dot sigma, let me write like this, is lambda G sigma 3 G inverse. I will finish this and then we will close. So the delta of S dot sigma is lambda times, I am making infinitesimal variation, so it is I lambda I epsilon dot sigma, okay, times it will be commutative with S dot sigma, right. Yes, yes, because this thing will come on one side and on the other side, and I will get this. Okay. So I can work out. It's just delta of S dot sigma is commutative. So by comparing coefficients, I get delta of Si is just I times it should be careful. This some slight delta Si sigma I, it just epsilons will come. It's equal to I epsilon I sigma j times Sj. Yeah. So this is I epsilon I j k sigma k Sj. Yes. So I find delta of Sk, let me write like this, is going to be I epsilon I j k epsilon I Sj. It's an infinitesimal rotation. That's all. Okay. Okay. So I now put it here. Delta L0 is a variation of that one. There is an I here which I am not happy. Where is this I coming from? There is an I here. There should be two I's. I here epsilon, there is an I squared. Here I squared is minus. Okay. So you find delta L0 is mu times minus mu times epsilon I j k epsilon I S j bk. So I get the equation of motion implies delta L equal to 0 if yes.
Like Nodal's,
Huh?
Nodal's force.
Yeah, this is spin. This is the equation I want, right? Because I have the epsilon dot term here, except for factors of 2, which I won't bother. I guess I won't bother. Okay. So this is giving Si dot from there. Okay. I am wondering where the factor 2 came from. Maybe there is an I lambda over 2. Let me see.
Maybe sigma 3 by 2.
One second. Oh, I know. I know. This commutator has 2 mu epsilon I j k, okay, s j b k equal to 0. This is what we want. Okay. We want a spin to rotate the magnetic field in this equation. I got this in the Hamiltonian way. So I am getting the correct equations already. Okay. So this funny looking Lagrangian, which has it's a Lagrangian not in your configurations, not in the physically realizable set of degrees of freedom. Okay, it has an extra degree of freedom, is giving the right equations of motion. Whereas if you try to find a Lagrangian which only involves a spin variable, we are unable to do it. We cannot do it. So this Lagrangian is very peculiar. Okay, so let me say a few words, then I will stop. Gauge properties of L. Okay. So let us focus on L Vesuvino. Because that is a funny thing. Okay. So I will just say a couple of words, okay, then we will continue. It changes by under this transformation g of t going to g of t exponential I sigma 3 theta of t. It actually changes. Since it is changing, yes, but it changes. So it cannot be written as a function of S and S dot. Because these things don't change. So it is impossible to write it like this.
Can you explain this little? What S naught?
S dot ds dt.
No, what is the statement S?
S is a spin variable.
What cannot be written?
This Lagrangian or this one
No, what is written here? L.
L Vesuvino
Oh, okay, okay. There is the S not there, so I was confused with that.
cannot be. But I can ask another, can I gauge fix? Can we gauge fix? What does it mean?
Well, again, I just how can you say cannot be written? So it changes on a G.
So as it stands is a function of g and g dot.
Yes.
If it could be written as a function of s and s dot, it cannot change under this transformation because s and s dot don't change. Okay. So as a consolation prize I can ask this thing, what does it mean? That is, for each s, okay, can we find a GS? So this G depends on S such that, okay, the spin is G sigma 3. GFS sigma 3 GFS inverse. So for each spin I find a G, because this theta is not doing anything. So I and put this GFS back in L Vesumino. Then I will say that I have got rid of this extra degree of freedom. The answer is no. Why? Because if we can do this, suppose I can do it, imagine, okay. Then every G is of the form GFS times some phase exponential I theta of some phase. Okay, the extra thing is here. But this implies that SU2, which is topologically a 3-dimensional sphere, this will show is for each S I have found a G is S2 cross S1. Right? This is impossible, because right hand side impossible, since left hand side is simply connected, that is, if you, it's a sphere, so if you draw any closed loop, I can, right hand side is what? What is the connectivity of the right hand side? Is infinitely connected, because this S1 because of S1. S1 is a circle, so I can draw loops around it. Okay, so I cannot do this. So here we have a situation where the Lagrangian lives on SU2, whereas equations of motion live on S2. Okay, and we cannot avoid this situation, namely I cannot simplify the Lagrangian and make it live on S2. Okay, so we have here, so the gauge invariance, gauge I should say covariance, okay, or sometimes is called weak gauge invariance. Of this L Vesumino is highly non-trivial. We will develop this theme further. Okay, we will see that this incorporates our first example of a fiber bundle, okay, a principal fiber bundle. I will show you how the principal fiber bundle is coming here, and we will see then the general structure of a principal fiber bundle already here, a U1 bundle. But once you know understand the U1 bundle, the geometry of the U1, how U1 bundle comes, then it is very easy to generalize it to more complicated fibers. The fiber here is U1. For more complicated discrete groups and so on, we can do easily. Okay. So I will do it next time. Okay. But if you have questions, I am available now. Yes.
Sure.
At the beginning, at some point, you said that you can write down not clear to me. I mean, how have you enhanced the degrees of freedom? Where is your enhancement of degrees of freedom?
There is one more degree. Is 3. G has 3 degrees of freedom,
Oh,
whereas equidistant motion only 2.
but you are still working on S2.
No, not the Lagrangian. Lagrangian is working on S3. And I cannot, I am unable to get rid of the extra degree of freedom that is coming. It is there, it is stuck. It is coming because if you know differential form, the volume form on the 2 sphere is d cos theta d phi. Right? If you try to write it as d of something, you will not be able to do it. If you take d cos theta d phi, it's a 2-dimensional sphere, so d of that is 0, right?
D of that
So
whole thing
is 0 because it's 2-dimensional. So it should be a d of something you would expect. Impossible, because if it were d of something, integral will be 0 by Stokes theorem. But it is not 0, it is 4 pi. So you cannot do it. So what we are doing is, by some trick, if you know differential geometry, well, these are differential forms. This is a good exercise. The volume form, okay, you can prove is d of I trace sigma 3 G inverse dg. What? But this G is not, it's not living here. Okay, cannot be d of some one form on the 2 sphere. This is not possible. This cannot be like this, because if it were, I integrate here, I get 4 pi, integrate here, I get 0 by Stokes theorem. So this is not possible. But by enlarging and going to one higher dimension, it is in fact possible to write this like this. Okay? This is due to some deep result, due to generic result, due to Andre Weil. Okay? And that is what is used by them in representation theory to get rid of this form and do some analysis. They don't do the analysis like physicists do, but for them this object comes that way. It's called the Maurer-Cartan form. It is an example of, I can give a language, it's called the Maurer-Cartan form. So this is what we are using in the Lagrangian. But that activity, that proof requires some, no, I will not do it, because it involves some further structure analysis of these bundles, which they did. Okay. Is that okay?